So where we were with the hydraulic fluid, you can do a lot of work with a small force, just by having a small area. Pressure is load over area. So you can do a lot of work on a big area with the same pressure, that you only need a small area to make it work. Okay, as you can see in this diagram, like a jack. Small load by hand, small area, you can lift a car or a truck or something. Hydraulic pressures usually run about 100 to 400 bar, very high pressures. So we have pressure in the system, and because of that, you're doing work very efficiently. Basic parts of the hydraulic circuit: you've got a pump at the bottom there. Then you've got what's called a pressure control valve. It's actually a relief valve, which extra fluid can pass through. We'll come back to that. And then above that, there's a direction control valve or a spool valve, directing the flow of pressure fluid to, at the top, a hydraulic motor or a hydraulic cylinder. And you can see the one side, it's pushing the cylinder one way, the other side would be pushing the cylinder the other way. And if it was a hydraulic motor, you could run the motor backwards or forwards, depending on which side you have send the fluid to. The pressure in the system is controlled by the work, the resistance on the cylinder or the motor. That determines the pressure in the system. And then what they've called the pressure control valve is a relief valve. That is there just to prevent, if your work sticks, if that hydraulic cylinder is pushing and it sticks, instead of it exploding, the relief valve would be actuated. So it's just a safety valve. And then you've got a filter built into the system. So just going through very quickly the different types of hydraulic pumps. That's a vane pump. It's steel on steel. The application is steel on steel. So your hydraulic fluid has to be, and you can see those vanes are very thin on the end, and so they are sealing between the rotor part. The white part in the middle is rotating and carrying the fluid around the outside, and it must seal. So the vane. Let's see. These are the vanes. As this rotates around, oil is trapped between the two vanes and is carried from the one side, from the inlet port to outlet port. And there are two inlet ports and two outlet ports on this pump. So on the tip here, there's very high loading, very similar sort of loading as you get in gears, in a gearbox. So a hydraulic, and it's steel on steel here. So a hydraulic fluid has to carry the same sort of loads as a gear oil and be compatible with all the other things that we're going to look at. Here's a gear pump. The fluid is just circulated as the gear turns. It's just trapped between the gear teeth and the housing and is transported around. So the pumps do not generate pressure. They're just transporting fluid. The work that's doing generates the pressure in the system. Variable displacement piston pump. Here, this whole section, the barrels are rotating, the pistons in them. The pistons are locked onto this, what's called a swash plate, which is at an angle. So as this barrel rotates, the pistons rotate against that swash plate, and it pushes the pistons in and out. So there's a pumping action. These will run very high pressures. And again, this is steel on steel, but not much pressure there. Here there's high pressure, and that is a phosphor bronze, what's called a slipper pad against a steel swash plate. So here you've got to have a multi-metal compatibility. You cannot have the same sort of EP additive, although the loads are the same as in gears, but you cannot use the same sort of EP additive as you have in gears.
Where is the hydraulic fluid in this? Where is it?
That is the suction side, that's the pressure delivery side. So the hydraulic fluid is coming in here, okay. And as this section rotates, it will suck the fluid in. That gets smaller as it's coming round, well, from here, as this rotates around there, this will push out, so that's delivery of fluid. And then when it comes down the other side, it will suck fluid. Okay, and then these plates here are your valve plates that control where it's sucking, blowing, the direction, sucking from there, blowing to there. Okay, this is just a hydraulic motor. Again, phosphor bronze components and steel on steel components. So the fluid has to be compatible with phosphor bronzes, coppers, things that a gear oil, the EP additive in a gear oil would react with. Hydraulic fluid, you cannot react with it. So it's a different type of extreme pressure additive you have to use in hydraulic fluid to a gear oil. This is just a hydraulic cylinder, and the only reason I've included this is because of the seals in there. The fluid has to be compatible with whatever seals you've got in the system, and all the hydraulic pipes and things. Those are polymers, and the hydraulic fluid must be compatible with all of those different types of, nitrile seals, whatever. The relief valve is just there to relieve extra pressure. The spool valve is now directing the pump, the pressure from the pump to one side of a cylinder or the other side, or one side of the motor, or different parts of the system. And the only reason I've included that is because, where is this here? This has to move left to right, right to left, to allow pressure, direct the pressure from there to there, or there to there, and at the same time the other return pipe back to the tank. The blue is low pressure back to the tank. So you have a clearance between the spool and the housing, and that clearance, because it's a clearance, the hydraulic fluid will pass there. It will leak past there in service. And so viscosity is critical, and the fluid must be clean. Otherwise, particles in there will get filtered out as it's leaking. Particles are the same size as the clearance will get filtered out, and then it locks that spool in place. And it's a big failure in hydraulic systems. They claim the fluid doesn't work. It's not the fluid that's working. It's the dirt they put in the system that's making it not work. Okay, the hydraulic tank is quite a critical thing, but we're not into tank design, so I'm going to skip this. The piping must always be specified that you have laminar flow in the pipes. You don't want too fast a speed of the fluid coming down the pipe. you've all been to the beach, okay? You see a wave coming up, and you see the water wash up, and then when it's washing down, you see that smooth, the water's smooth, and then suddenly it starts going rough, and then it goes smooth again. That is the critical speed for water. It will get to where the speed, the rate of shear, is such that it suddenly becomes rough. It depends on Reynolds number. It's a scientific term. Okay, you can get the same in a pipe. If the speed is above a certain speed, it will suddenly start getting turbulent in the pipe. And then there's huge resistance in the pipe. So you always want a slower speeds in the pipes. And in a normal hydraulic system, it should never be more than 4 to 6 meters per second. Must not be faster than that. If it's faster than that, you will have turbulence and the system won't work properly. No matter what fluid you put in there. You know, they tell you wrong fluid. It's not that. It's design of the system. On the suction side, it must be about 0.2 meters per second. Okay, now looking at hydraulic pump efficiency, the pump manufacturers quote a nominal flow rate for the pump, but the actual flow rate is a function of speed, pressure, and temperature. And it depends on the pump's volumetric and mechanical efficiencies, and those depend on fluid viscosity. So if you look at a pump, the pump might be a nominal 100 liters a minute, but what's coming in, the actual here, and going out, actual might only be 80 liters. So inside here, it's transferring 100 liters, but 20 liters is actually leaking inside the pump from the delivery side, the high pressure side, back to the suction side.
Oh, it's a closed system. Oh,
it's a closed system, but you've got clearances in the pump.
So kind of stays there.
So the fluid, yeah. So the fluid is, if you've got a vein, the vein is in the against the housing and against the rotor, and some fluid will get past the vein there and some past the vein here because of the clearance. Now, that how much passes depends on the viscosity. Higher the viscosity, the better it will seal. So viscosity is critical to make the pump run as efficiently as possible. And we can see from this that the y-axis is pump efficiency, the x-axis is viscosity of the fluid. You can see that below 10 centistokes, that's 10 centistokes, below a line there, the pump becomes very inefficient very quickly. Above that point, you're above 80% efficiency and the pump is more stable. Ideally, you don't want a viscosity below about 20 centistokes. Okay, so the minimum viscosity you want for a hydraulic fluid in service at operating temperature is 10 centistokes. For our ambient conditions, a 68 ISO is considered best. That's the best performance I've had. Okay, but looking at this now, the importance of correct viscosity, if you look the volumetric efficiency, if this is efficiency on the y-axis, viscosity on the x-axis again, if you have no viscosity, then your volumetric efficiency will be 0 because there's nothing to pump. On the other hand, your mechanical efficiency is 100% because there's no back pressure. So your mechanical efficiency starts 100% with 0 viscosity and drops down. And the mean of those two graphs is the actual pump efficiency, what it's going to be. So that's the actual pump, overall pump efficiency. We'll follow that red curve. And so you can see that is the viscosity that you actually need for this pump. So it's your optimum operating viscosity between 12 and 100. So 68 is nice in there.
And what are you sacrificing if you choose 46?
Okay, 68 you'd be operating here, 46 you'd be operating there, 32 you'd be operating here.
Those would be, but then 46 appears to be more efficient because overall efficiency, the red dots are
Yeah. It can be, but then on a hot day, it moves from there to there. And it can move there, and then Wirtgen equipment, you know, those machines that take the tar off the roads to recycle it? When they first came to the country, the requirement was 46 ISO, finished. Germans, very, very easy to negotiate. And on a hot day, the machines would be running here, and no matter how fast you ran the pump and the engine, you would get no work out of the machine because all the fluid was just circulating in the pump because the viscosity was so low. And changed them from a 46 to a 68, solve the problem. You're then working, instead of working here, you're working there using a 68. The industry, I did that a long time ago.
So basically it's safer to go with higher viscosity in South Africa.
Yeah. Okay, and then this is comparing a normal VI of 100 to a high VI fluid. You can see here a normal VI of the dotted line for a 46 would have a maximum operating temperature of 80, and whereas a high VI fluid, I don't know what the viscosity index is here, but maybe 150, you could operate up to 120 degrees C. So here you can see for actual pump temperature of 80, which you can reach on a hot day, the 46 will be useless. Okay, this is just looking at clearances in the hydraulic systems between 0.5, 5 microns, piston pump, piston to bore as much as 40 microns, but that's the most. Otherwise, it's typically 0.5, 5 micron around there. And so that is dirt in the system. Dirt particles that big are going to clog the system and cause damage. So that's why you have to keep hydraulic fluids as clean as possible, always. And the benefit, if you can supply a cleaner fluid than your competitor, for hydraulic fluid, that's a benefit. And the mines, not optical, but the big mining companies actually filter the fluid into the machine. They don't trust what comes out of the drum. Okay, hydraulic fluid formulation, you've got to have the correct viscosity, high viscosity index, multigrade hydraulic fluid is better because it makes the system more efficient. You've got to have good rust, corrosion, low volatility, anti-wear, very good anti-wear, low foaming, good air release, all those things, and compatible with seals and all that sort of thing. So the hydraulic fluid performance is there are many tests that the OEMs and the classification people use to control hydraulic performance. There are load carrying tests, the 4-bore. There's an FZG test, which is gears, actual gears, like for a gearbox. It has to meet that requirement. Pumps, the Parker Hannifin Denison pump is the most severe test there, and then filterability, elastomer compatibility, seal compatibility, and all the other tests. The actual test standards for each of those, and if you're going to have your hydraulic fluid approved, you must meet all of that. The basic performance is the DIN 51524. HL is mineral oils plus a rust and oxidation inhibitor. HLP is HL, so rust, oxidation, and anti-wear performance. And then HVLP is rust, oxidation, anti-wear, and high VI. So that's the standards there. And that is the basic performance that the hydraulic industry needs.
High VI is multi-grade.
Multi-grade, yes, yes. A VI of over 100. So 140, 180, yeah. Now, the pump manufacturers would require DIN 51524 plus their own pump tests, or their own tests, which could be filterability and all sorts of things. And Parker Hannifin HF0, it used to be Denison HF0, is considered the most severe specification of all pump fluids, hydraulic fluids. So if you have an HF0 approval, it will run in any of the other systems. You know, the Vickers is quite a high spec. Cincinnati's not so great. And now if we look at HLP, Gazprom Neft Hydraulic HLP, you'll see the features: enhanced wear protection, so it meets the requirements, the pump requirements, superior cleanliness, that means it's got good oxidation stability, it will not oxidize in service and cause deposits in the system, so it keeps clean. Excellent thermal oxidation stability, okay, we've just said that because it keeps clean. But of course, they put it separately because most people don't understand that. Corrosion protection, it has to do compatibility with all the common seal materials, and fast air release and low foaming. So that's the features. If we look at the performance against these specifications, DIN 51524, which was anti-wear performance, oxidation, rust. It meets for all the grades and meets the requirements for different manufacturers here, depending on their viscosity requirements. And then actual approvals, Bosch, I left out Bosch Rexroth one here.
No, it is there. It is there.
It is, okay.
32, 46, 68.
Yes, okay, okay. Battenfeld, they only approve a 46, but meets whatever other viscosities different. Denison, HF0, everything, but the 100, it meets the requirements if they approved 100 grade. Vickers, the same. So you can see it meets all the major manufacturers. It's an excellent oil. Oxidation stability, rust, load carrying, wear performance, does it all. And there's just the lab specs for the different grades. You can see the viscosity index is 100. Flash point, just increasing flash point with increasing viscosity, you would expect that. And with increasing viscosity, you have a decreasing viscosity index. Total acid numbers are the same because one package. Cleanliness, 1513, is pretty good. That would be a guaranteed cleanliness. To guarantee that, the drums you buy are probably about a 1210, 1310, something like that.
Clean drums,
yeah. Clean system. And then I've just included this, which we've looked at before. It's G Special Power HVLP, so you can see it's a high VI. It's oxidation, meets oxidation, rust, load carrying, and it's a high VI fluid. And with this particular one, you can have increased productivity, 15 to 25% in a hydraulic, like an excavator, or reduced fuel consumption about 6%, which is significant. You can imagine some construction equipment running with better productivity and lower fuel consumption because of viscosity. Okay, that's hydraulic fluids.
That was pretty quick.
Yeah. So, any questions on hydraulic fluids? Sorry?
You give different groups. You give group 1 hydraulic and
Yes. Okay. Okay. A group 1 is only the type of base oil that's in there. Okay, it's a group 1 base oil. It can meet, and then a group 2 is a group 2 base oil. If they both meet the same requirements, like Denison, Parker-Hannifin, HF0, then they're both going to perform pretty much the same in service. There is an argument that says a group 2 will have better oxidation stability. I haven't seen that in service. I mean, it's never been proven to me. The negative on a group 2 is it's like water. You can't see a leak with a group 2, whereas a group 1 has got a bit of color to it and you can see it leaking. Yeah.
Why not use some dye in group 2?
Well, to be quite honest, there's only one company in South Africa that I know that has a group 2.
Which one is that?
And yeah, they're one.
Stekel.
No.
Stekel
No.
is not one.
No.
Castro.
No.
You can say names. It's okay. We are more friends.
It's Chevron.
Oh, yeah.
And in the mining industry, they were forced to dye the oil to show leaks.
Really?
Yeah. It was a major problem for them.